Hello again. Welcome back to Physics 1. In this video, I want to introduce the concept of acceleration. This is a term we use in everyday life. Just a little warning, we use in everyday language, we use words acceleration and sometimes we say deceleration. In physics, we will never use deceleration. Instead, that scenario, we will just say that the acceleration was negative. And that avoids problems by saying a negative deceleration would be a positive acceleration. We just avoid all that. So we always talk about acceleration. So what does that refer to? I think you kind of have an intuition for that. You get in a roller coaster, you put the straps down and buckle in, you're ready to go, and you are, maybe if it starts quickly, you would accelerate and take off, or maybe an aeroplane, right? Accelerate, take off. All right, that's the idea. But we're going to unpack that and be more precise. So in the last video, we ran through an example with some scenario where there was a train, and it started from rest, and then it increased its velocity to some amount, and it coasted, it maintained the same velocity for a while, and then the velocity went down to zero as it came to rest again, okay? So those were scenarios where the velocity was changing with time. That's what acceleration measures. Acceleration is going to be the rate of change of velocity with time. So remember, velocity itself was the rate of change of position with time. Acceleration is the rate of change of velocity with time. Or verbally, if you kind of follow this, it's the rate of change of the rate of change of position. So it's a double rate of change. Okay, that's what acceleration is. So we're going to have a scenario here with a cart, so you can kind of see, and then we'll go through and define acceleration more precisely. So here's a situation. I get it lined up there. Okay, so the cart starts at zero. I'm going to start here. At zero, it's the same zero we used before. And then you'll notice I put a notebook underneath it and making the track sloped. But look what it does. So it starts from zero. I'm going to remove my hand. At that very first moment, if I can do it really quickly, it doesn't move much. In fact, that very split second I let go, the velocity is zero. It's going to start from rest. And then it's going to start moving to the right. Well, if the velocity is zero, and a moment later it's moving to the right, then the velocity is increasing because to the right is a positive velocity. So it starts with no velocity and finishes with positive velocity. So it gained velocity, right? So here we go. Exciting. So it starts from rest and then gains velocity in that scenario. Okay, so let's go through that. I think I'm going to move this track. I'm afraid the camera's going to focus on it. So I'm going to move the track, and if we need it, I'll get it back. All right. So let's try to sketch a velocity versus time graph for that scenario with the track, with the cart going down the ramp. So in that scenario, okay, we're graphing velocity versus time, not position versus time. That'll come later. Equations. Or in the lab, we'll do that too. Okay? And then let's think about what happened. At the beginning, the moment I removed my hand, the velocity was zero. And as time progressed, it moved with an increasing velocity. It started moving to the right, and the velocity grew and grew and grew. So it turns out, and it's hard to, the exact shape of this, you have to just trust me, but it is true. We'll see this when we do our labs. In that situation, if I were to graph the velocity, it would start at zero because it started from rest, And after a little bit longer, it would have grown. And in fact, if I do this right, a little bit of luck, this should be a linear graph. The velocity should have been linear. Okay. And pro tip, if you're making a graph in front of people, you can't fix it, just make the dots bigger. You always look good. All right. Well, better would have been to draw the line first and then mark the points. Okay. Now you have to take it on, I guess, on faith that that's actually what the curve would look, that it was linear, but it certainly increased. That should be without question. Okay. So here we have a velocity versus time graph with a changing velocity. The quantity, mathematically, the object or the thing which measures changes or rates of change is a slope. So the slope of this graph, which would be the change in velocity over change in time for the average slope anyway, is what's going to be called acceleration. So the slope of velocity versus t, versus t, is acceleration. And the slope of velocity versus t, time, is acceleration. More precise, or maybe useful here is to say that the average acceleration between any two points in time would be the change in velocity over the change in time. Remember when we had average velocity, it was the same kind of formula. And then for a linear graph, that's fine because the slope, the average slope is the same as the instantaneous slope. But if we had a bendy curve, we'd have to define an instantaneous acceleration. And that would come from, remember, drawing the secant line and letting the points come together. And you would get a tangent. So you would find the slope of a tangent line at a point. So the instantaneous, you get the instantaneous acceleration, and as with velocity, I won't write INST. That's going to be the slope at a single moment in time. Now, here's the other little, the other example. For almost all examples we will talk about, the velocity versus time graph will be linear, or at the most, it'll be portions which are separately linear. So it'll be one line connected to another line, connected to another line, like in the train example we had before. Not until we get to oscillations or something like that, would it not be so simple. So anyway, so you don't really, for acceleration, for us, you really don't have to worry too much about the difference between average acceleration and instantaneous acceleration, as long as you are in a straight line segment, because they're the same for straight lines. All right? So the slope here, slope of velocity versus time, equals the acceleration A. Okay, let's talk about units. The slope is the change in velocity over change in time. So if you're thinking about units, we already saw that the units on velocity were meter per second. So the units on acceleration would be meter per second. So meter per second squared. That's a good thing to know. The units of velocity are meters per second, and therefore the units of acceleration are meters per second squared. That's a good check when you do a problem. If you put in all the units correctly, then it should make sense. So if it doesn't make sense unit-wise, then you know something is off. Okay, that's great. And it's really, other than changing spelling, this is the same relationship we had between position and velocity. Only now we're talking about velocities and accelerations. And no surprise, we have the other following relationship. Because the relationship between velocity and position can go forwards or backwards, well, guess what? The relationship between acceleration and velocity can go forwards or backwards too. We also have that the area under the acceleration versus time graph gives the change in velocity. Remember, we had that the area under the velocity versus time graph gave the change in position. Now we have that the area under the acceleration versus time graph gives a change in velocity. So let's kind of summarize all that in a nice little, I guess, table here. The slope of position versus time gives, sorry, how did I write that? Sorry, position versus time graph, there you go. Using the slope gives velocity. Now, if I have the velocity versus time graph, and I work backwards using the area, I find the change in position. We've seen that before. What we're adding now, using the concept of acceleration, is that from velocity versus time, looking at the slope of that, you can get acceleration. And from acceleration versus time, that was slope, you can work your way backwards using area, and that's going to give us the change in velocity. So it's kind of like rungs on a ladder. You can kind of go from position to velocity and then velocity to acceleration, or you can start with acceleration to get to these changes in velocity, and then from there you can try to work towards position. Or you can start with the velocity and work up to get position and down to get acceleration. So we have these three quantities, and they all have kind of an intricate connection. I want to finish by using the cart. Having gone through the derivations, I want to use the cart and go through some scenarios and hopefully help you see how things kind of fit together. Okay, so I'm going to bring the cart, the ramp back. Okay, and what we're going to have here is a situation where the cart is going to start here, and I'm going to push it to the left in the negative direction. Okay, so it's going to start out with a negative velocity, because I want to push it to start it out. It's going to go up the ramp. It's going to stop very briefly, just for an instant. So in that moment, though, the velocity will be 0, change directions, and then return back down the ramp. Let's see that. Okay. So I start, my velocity is negative, reaches the top, changes direction, and then comes back down. Okay. So let's try to graph that situation. See what happens. So in that situation, we could graph graph velocity. Let's start with that. We have the most information about that. Okay. So at the beginning, the very beginning, the split second after my finger is there. And that's just a comment. In this class, we make very simplified models for real things. And so I'm never going to ask about the details of when my finger was pushing it, or I'm never going to ask about the details during, when we throw an object. I'm not going to ask about when it really is in contact with the ground. I'm always talking about the kind of split second right before collision, that kind of penultimate moment. That's what the kind of thing that I do. All right. So anyways, in this situation, this initial velocity is negative because it's moving to the left at the beginning. It reaches the top. At the very top, the velocity goes from negative to positive. It changes direction from negative to positive. And then it finishes going down the ramp. That's in the positive direction. So let's graph that. The velocity starts negative. And then at some point, it went from small and negative to small and positive. Right? Because it's small velocity and negative to small velocity and positive, and then it became more positive. And finished with a velocity here. So what I want you to be able to see is when it changed directions, the velocity must have been 0. Okay? It went from small negative to small positive, changing signs, had to pass some 0. And if I do that, hopefully it's a nice and straight line. Again, see, maybe I'll get lucky this time. And yeah, no, they're not even close to being on a straight line. So we do that. And we quickly erase that before anyone notices and put a dot there. Okay? So this would be at the start. This would be when it changed directions. When the direction changed. And this would be when it got back to the initial point. Back to start. Okay. Now, first off, let's think about acceleration. Okay, started here, up, stopped, and then came back. What did I say was acceleration? Acceleration is the slope of the velocity versus time graph. Acceleration is the slope of velocity versus time. My velocity versus time graph describing that motion. And I see that that slope is positive. It's always positive. Velocity was negative and then positive, but the slope was always positive. So in fact, acceleration is always positive for this motion. I'll show you another situation. That's kind of confusing, isn't it? Think about what happened to that cart. I use a word that I've avoided saying. Started out moving fast. That's the word I haven't even been using. And then it stopped. And then it sped up again. Okay. Most people aren't bothered by the speed up part, saying that that was a positive acceleration. But people are bothered by saying that, wait a minute. It started out moving fast and then came to a rest. It slowed down. But what I'm telling you is the acceleration was always positive. How can that be? The reason is our everyday language is failing us. In everyday language, we say we accelerate when our speed increases. I haven't even yet defined speed. You know what you mean. That's not right. Or at least that's not the definition of acceleration in physics. Right? The definition of physics isn't connected to speed or fast. It's connected to velocity, changes in velocity over time. And so what happens is, in this situation, it started with a large negative velocity, going up the ramp fast, quote unquote, but a large negative velocity. And then it got to the top and its velocity was 0. So the velocity went from a large negative number, so like, -5, making stuff up. And then at the top, at the peak, the velocity was 0. Well, if you start at -5 and you finish at 0, you gained velocity because 0 is bigger than -5. So in fact, as it went from a velocity of -5 going up the ramp to 0, that's a positive change in velocity, and hence you get a positive acceleration. On the way down, no one's bothered by that. Velocity starts on the way down at 0, and then it gets +5, right? So it grows in the positive direction. No one's bothered by calling that a positive acceleration. But this is a scenario, the one I just showed you is a scenario where the acceleration is always positive. Let's do another one. I'm going to move the notebook. We're going to do the same basic experiment, only this time I'm going to push it the opposite way. So in this case, it's going to start, and I'm going to push it. So the split second after it leaves my hand, it's going to be moving to the right with a large positive velocity. It's moving to the right. And then it's going to go up to the top. It will stop briefly, change directions, and then go downhill. Ready? Okay, let's think about what we just saw. It started with an initial velocity moving to the right, went up the hill, stopped briefly, and then went downhill. So if we think about that, that means for this scenario, if I graph velocity versus time, at the initial time, it was, the moment after my hand left, it was moving to the right. So that would have been a positive velocity. So initially, the velocity was positive. And then went up the ramp. When it went up the ramp, it went until it didn't go anymore. So it stopped briefly, it changed direction. So in that turnaround point, the velocity was 0 as it switched from positive to negative. It changed directions. And then it was a negative velocity after the fact. And what is this? And again, I claim without proof that it would follow a line for that path. Okay, so this is a scenario. This is a velocity versus time graph that plausibly describes what we saw, and I claim, in fact, it's an accurate representation. Now, what about the acceleration? When I look at that, well, from a velocity versus time graph, the slope of velocity versus time gives me acceleration. Acceleration is change in velocity over change in time. So that is, well, it's negative. It's a negative acceleration. How can that be? How can the acceleration be negative? Let's think about that. Well, in this case, again, in this case, so I push it, initially the velocity is positive, and it comes to the first part, it comes to a stop, right? So in that first segment, starts with a big positive velocity, comes to a stop. Nobody complains that that's a negative acceleration. That makes sense to everyone. But what about the turnaround part? So it goes up the ramp, comes to a stop, and then comes back down. Think about that. When it was going uphill, we all agree that the acceleration was negative. That seems intuitive. But what about when it was going downhill? It started with, on the way down, the beginning point then would have been at 0 velocity, and the finishing would have been when it was going to the left. So the velocity would have been negative, say -5. Just making up a number, but it would have been negative. So on the final segment, as it is going downhill, when the velocity was negative, the velocity started at 0, finished at -5. So the change in velocity would be something like -5 minus 0 over the change in time. That's it. So a negative minus 0, that's a negative number. So in fact, the acceleration was negative. So a positive acceleration either means a positive velocity is growing, but it could also mean that a negative velocity is getting less negative. And a negative acceleration could mean that a positive velocity is becoming less positive, but it could also mean that a negative velocity is becoming more negative. To think about that, it's a little bit tricky. So go through, and I want you to think about various situations. So when you get to class, I'm going to have you guys do this, but I want you to think about it. Think about what it would look like to walk, maybe with, with a positive initial velocity and a positive acceleration. What would that look like? So let's see. Start out moving in the positive direction and have a positive acceleration. So that would mean my positive velocity is going to get more positive. So I'm going to go faster, 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 splat into the computer. Or what if you start out walking with a positive velocity, but you have a negative acceleration? So that means that every moment in time, you're losing velocity. If your acceleration is negative, you're losing velocity every moment. So I would start out moving positively, but then I would lose, get to 0, just to change direction and go the other way. Then you would lose more and more and more until you splat into the wall. Okay? So think through what it would look like if you started with a positive velocity and you walked with a positive acceleration. If you started with a positive velocity and walked with a negative acceleration, and then do the other. Imagine you walked with a negative initial velocity and a negative acceleration. And imagine what it would look like if you started with a negative initial velocity and you had a positive acceleration. And after you do all this imagining, I want you to get up and I want you to try it at home and see if you can explain it to someone. If there's someone else in the house, explain it to them, because I think in the process of explaining it to someone, it'll force you to sort out the minus signs and you'll understand what I was just showing. Okay. Very good. So this was acceleration and velocity versus time graphs and how they're related. I'm going to, in the next video, I'm going to address the everyday language that we use, but I haven't touched yet. I mean, speed, and fast, and distance, those are words that people use in everyday language that I haven't yet used in this class, or I've tried to avoid in the next video. And then in the video after that, I'm going to use all of your great mathematics skills to turn some of these graphs and simple shapes that we've been having, and we're going to mathematize them and get equations. And they're going to be kinematic equations that we will use all semester to analyze motion. So they're going to be really important things for you to understand and know how to use. So, all right, see you next time.